Welcome everybody to your 13th lecture on Earth science. This time we're going to be talking about glaciers, and I hope you had a good spring break. I know this is your second lecture after you get back from spring break, but we're getting back, getting the ball rolling here. You had actually not streams, but groundwater last time. So normally we talk about streams and more about lakes and things like that too, but we missed that because of the winter freeze. So anyway, it's all right. We're going to be doing glaciers today, and after that, we're going to, I think, move on to, if I'm not mistaken, I think we're going to move on to the oceans next week. So anyway, we'll get started here. So you have this initial picture. You might know that a lot of glaciers around the world are receding. Doesn't mean they'll recede forever. Doesn't mean that they will necessarily go away. We don't know exactly what's going to happen in the future. But for the time being, they are quite a bit are receding. So this is a pretty famous picture. This was taken in Svalbard, Norway in 1928. And you can see a very large glacier here in Svalbard. That has now, you can see, you all see how the picture is exactly the same. You can see the outline of the mountains here in the background. It's exactly the same. But you can see that what's happened is the glacier is now missing, right? So it's receded, and actually it's right here now. This is the glacier where it is now at this time. So it's receded quite a bit back into the mountains. So they are receding in a lot of places, not everywhere, but in a lot of places. This is a pretty shocking picture, I think. This is the Muir Glacier in Alaska, 1941. And you can see this valley is totally filled by glacial ice. And you can see what the valley looks like now. And look, I mean, the ice was very deep. You can see how deep it was. I mean, this was a vast valley filled with glacial ice. And now the glacier is receded back to here. So this is the glacier at its present point now. And actually not even present. This is 2004. Here's the Grinnell Glacier National Park in America. I don't know if any of you ever been to Glacial National Park. I've actually never been to it myself. I had a chance to go, and I decided not to because that summer that I was supposed to go, somebody got eaten by a bear. So it kind of put a damper on things. But most people don't get eaten, so it's a good place to see. I didn't feel like I was visiting around Yellowstone and things like that in that general area. So I didn't end up going, but I probably should have gone. Anyway, Glacial National Park is a place in America. You can still see glaciers today. There are a lot of places actually. There are glaciers. We'll go over that in a little bit. But 1910, this is what the Grinnell Glacier looked like. 1931, you can see it's starting to wane a little bit. In 1997, you can see that it's receded quite a bit, because you can see this part of the valley was all filled with glacial ice, and now that's mostly meltwater in 1997. So it's been happening for a long time. This is a slide that tracks glacial mass balance, kind of how much glacial ice the glaciers are adding or subtracting year after year since 1970. So you can see that if the dot is red and big, it means a lot more glacial ice has been lost. If it's blue, it means that it's actually been added to. So you can see that there are some blue dots, right? You can see in Scandinavia, actually, there's quite a few blue dots. So those are areas where glaciers have actually grown. There's some growth in Greenland, some in Canada, right? So there are some blue. I mean, there are points where glaciers are growing, but more or less, it's a picture of receding glaciers. Some of them are very bad. This is New Zealand, has really receded, right? And the Andes Mountains, lots of recession. Greenland, lots of recession. So in the Alps, the Swiss Alps, Himalayas, there's areas where there's a lot of recession of the glaciers. Okay, so that's due to climate change. Whether you think it's natural or man-made, you have to face the fact that glaciers are receding. So this is another illustration of the South Cascade Glacier in Washington State. This has been a very carefully tracked glacier for a long time, since 1955, and this is showing how much ice, basically the mass balance, right? Either how much ice is being added or subtracted year after year. Some years it adds ice, right? You can see this here, 1959, 1971, 72, 96, 97, 2002, it was adding ice, but most years it's losing ice. And some years it's really losing a lot. 58, it lost a lot of ice. 87, it lost a lot of ice. Okay. So it just kind of paints maybe a fuller picture for you all. You probably hear things like glaciers are receding and glacial ice is melting. But it's not happening everywhere, and it doesn't happen every glacier every year, but the general overall picture is they're receding. Okay, so this is a picture of that glacier in 1958. Now this is what it looks like closer to today, and you can see it's lost a lot of ice. It looks like a muddy puddle now, so that's not good. So where do glaciers form? Basically they have to form, you can guess, where it's cold, right? So that can either be in areas that are high latitudes, right, near the poles, or it could be on top of mountains, okay? So at the North Pole and South Pole, you can have glaciers form even at sea level, okay? Once you get to like 60 degrees latitude, which is pretty close to the poles, remember that 66 degrees is the Arctic Circle and Antarctic Circle, right? So 60 degrees is pretty far north, okay? That's like Scandinavia, okay? You can have glaciers form not at sea level. It's not cold enough at sea level, but at 4 kilometers, it is cold enough, right? Now, what about at mid-latitudes, kind of, around where we're at? We're at about 27 degrees here in Corpus Christi. So to have a glacier here, you would need to have about what looks like 6 kilometers in elevation. Okay, it would have to be 6 kilometers high to get a glacier forming on a mountaintop. So 6 kilometers is quite a bit, right? So that's 6,000 meters. It's around 10,000 feet. So you'd have to have a pretty high mountain in order to sustain that. At the equator, you can have glaciers at the equator. It's possible, but they can only form on pretty high mountaintops. I'm talking more like now 7 kilometers. Okay. So that's how it is. We do have glaciers here in America. We have a lot, obviously, in Alaska. You can see that. These little red areas show where there are active glaciers. Okay. And we do have some, wouldn't it surprise you? We have them in California even. You probably didn't even think, wow, we have glaciers in California. We do. In the Sierra Nevadas especially, we have active glaciers. So it's kind of interesting. We have them all throughout the Cascades here. So these are the Sierra Nevada mountains in California. And these are the Cascades here, all through Washington State, Oregon, and Northern California. Okay. We have lots of glaciers there, right? So, and we have them too. I don't know why there's nothing in Montana, but we have some in Montana and Glacial National Park as well. Okay, and you know what? There's even some in Colorado. I guess these red blobs are really more expansive glaciers, but we do have 200 glaciers in Montana. Idaho has glaciers. Utah has a glacier. Nevada even has a glacier, right? So there are glaciers scattered throughout America all over the place. I don't know if we have any in Texas. That's a good question. Probably not. I don't think we have any elevation that's high enough to sustain a glacier. So let's see. I want to move on here. Now, we have 3 kind of general types of glaciers, and we're going to go through these types one by one. But I'm going to just introduce them here and now. So first of all, you got to know what a glacier is. This is really important. This will be on the test. Probably now it's going to be on your final exam. So you want to know this. A glacier is a mass of dense flowing ice. Flowing is an important word here. It might surprise you to know that glaciers flow. They do flow. Just like the mantle can flow in the solid state, so also glacial ice can flow in the solid state. So it builds up over many hundreds to thousands of years, even hundreds of thousands of years on land. Okay, So those are all really important aspects of this. First of all, glaciers have to form on land. Okay, it's ice that's forming on land. So we don't think of things like icebergs floating in the water. We don't think of those as glaciers. Okay, people are concerned about the melting of glaciers because that adds to sea level rise in a way that icebergs don't. Okay, so this might interest you. Maybe it will, maybe it won't. But if you have some ice, glacial ice, or not glacial ice, but you have ice floating in the oceans, if that glacial ice melts, I'm sorry, not glacial ice, but if that ice, like iceberg ice, melts, it's not going to contribute to sea level rise. So just like the same thing, if you were to put some ice in your, whatever beverage you're drinking, and the ice melts, it's not going to cause your glass to overflow. Okay, it's going to maintain an equilibrium. However, when you have glacial ice is actually sitting on the land, so it's not being supported. Its weight isn't being supported by the water or the ocean, so it's going to, when it melts, it's going to flow into the into the oceans ultimately. Okay, so anyway, that's why people are concerned more about glacial ice melting than like iceberg ice melting and things like that, and sea ice melting. So glaciers have to be flowing. They have to flow. They have to build up over many hundreds of years. That means that they can't melt every year. Like you can't have, there's no glacier that melts out. It's just seasonal. Okay, they have to be perennial. They have to subsist year after year after year. Okay, and it has to flow due to the force of gravity. So flow is a big deal here. All right, types of glaciers. Okay, we have three types. We have what are called alpine glaciers. They're mountain glaciers. Those are things that form at high topography, mountainous areas, and they flow down slope by the force of gravity. They can be maybe hundreds of meters thick. We have ice caps, which are regionally large permanent masses of ice that serve as a source for smaller mountain glaciers, but they're kind of larger than alpine glaciers. They're regional in size, but they're still smaller than ice sheets. Now, ice sheets are huge, expansive glaciers. They cover vast continent-sized areas of land, and they build up over tens of thousands of years. Some places, if you can believe this, there are some places where these are 5 kilometers thick with ice. So we only have 2 ice sheets. You need to know this for the test, so make sure you know this little fact. We have 2 ice sheets in the world right now, the Greenland ice sheet and the Antarctic ice sheet. Okay, so we'll talk about both those things in turn. We used to have, during the last ice age, we used to have more ice sheets. We used to have what was called the Laurentide ice sheet. I'll spell that out for you. You don't need to know this, but it's kind of interesting. The Laurentide ice sheet. And that used to cover parts of America and parts of almost the entirety, if not the entirety of Canada. So, up to all the way into Ohio, Michigan, North Dakota, parts of South Dakota, we used to have a ice sheet that was maybe 5 kilometers thick in certain places. Parts of Michigan, most of Michigan was probably buried under about 1 kilometer of ice at that time. So it wasn't that long ago. That was maybe 14,000 years ago. We had that Laurentide ice sheet. Okay, so just kind of interesting factoid for you to think about. So the way that this glacial ice forms is, of course, it starts off as snow. By the way, this is an old figure number. I don't use that book anymore. But you start off with snow, of course. Then after about a month, with increased compression, because what happens is the snow forms, and then more snow gets on top of it, more snow, more snow, more snow, and as it gets buried, the pressure increases, right? So the pressure goes up, right? So this is getting compressed. It's recrystallizing, and it's forming denser and denser and denser forms of ice. So snow that is not packed tightly, just caught, fresh fallen snow is really fluffy. I don't know if any of you got a chance to play in the snow. I guess we got a little dusting of it this year, but those of you who have really gotten to play the snow, you know that fresh fallen snow is very fluffy. It has actually 90% air. So what happens is as it gets compressed, that air gets pressed out. Okay. So as snow builds up, it builds up, increases the pressure. Sublimation is melting of the snow, reduces the air pockets, and it allows for denser packing. That's when you start to get crunchy snow. See, we don't have as much here in Texas. We don't have as much experience with snow. This is kind of easier to talk to students in Michigan about because I used to teach in Michigan, so they have a lot more experience with snow. But you might know the difference between fluffy, nice, fresh fallen snow and crunchy snow. Okay, so crunchy snow happens when you get a little bit of melting. So that melting can help to kind of fuse the snow grains together. And after about a year, you transform the snow into something called firn, F-I-R-N. It's densely packed snow that is at least a year old. It has less than 25% air now trapped in its matrix. Now, further crystallization, further burial, and further kind of melting and fusing of the ice together is going to create something called snowpack and glacial ice. Okay, so it looks like snow on top, and it gets denser with firn. And as you get deeper and deeper down, you'll notice that the ice starts to change color. It'll start to become more of a bluish color, and that's when you start to get real glacial ice, which is very dense, highly packed material. Okay, so just kind of a little recap about glacial ice. If it does not flow, it's not a glacier. Glaciers have to flow. Free-floating sea ice is not glacial ice. We don't consider that a glacier. Okay, so things like icebergs and sea ice, we don't consider that a glacier. However, there are things called ice shelves, which are basically extensions of glacial ice, continental glacial ice over the water. I'll show you some examples of that. Those, we do consider that glacial ice. So ice shelves are glacial ice. They're over the water. They aren't really floating on the water per se, but they are over the water, and they're extensions of the continental glacial ice sheets. Okay, but it's important to know that icebergs, we don't consider things like icebergs glacial ice. Okay, so this is a picture. These are pretty cool time-lapse pictures of taken over days. You can see I hope you can all see how the kind of the snow's getting light and dark. It's because the days are it's going night and day. But you'll notice that the ice is flowing, right? So you can see it flowing almost like a river. So this was taken over, many days. It's just a GIF of different glacial ice flowing, just like a river. It's pretty interesting. So if it doesn't flow, it's not a glacier. So let's talk about some of these things. I mentioned ice caps, alpine glaciers, ice sheets. So let's just first talk a little bit about ice caps. We only really have one ice cap. That's the Vatnajökull ice cap in Iceland. Like I said, it's just kind of it's a glacier that is maybe hundreds of miles or 100 miles across. It's not a huge, expansive continental size type thing, but they are very large. Okay, and they feed into all these alpine glaciers and feed into all these ice streams in other places. So that's the Vatnajökull ice cap. We have two ice sheets, though. We have the Greenland ice sheet and we have the Antarctic ice sheet. So you can see the Greenland ice sheet here at its thickest is over 3,000 meters thick. 3,000 meters. That's pretty amazing. That's like 10,000 feet of ice. Okay, so it's very, very thick ice on Greenland. Okay, and you'll notice that the ice is thickest here in the center of the island, and it gets thinner as you move out towards the shore. So you can see that there are mountains on Greenland, and the glacial ice is so high that you could just see the very tips of those mountains poking out through the ice in certain places. So it's pretty interesting. So here's the ice flowing in, from the high points here at the summit of the ice in the center of the country. The glacial ice flows out. It's moving downhill, and it flows to the sea. So that glacial ice is constantly flowing out. Okay, as it flows, it meets the ocean, and what happens is it cleaves off, and it becomes an iceberg. So you'll get all these icebergs from what's called, there's a process called calving, glacial calving, and it calves off these icebergs as the glacial ice flows from the summit into the ocean, okay, because it is flowing. So that's how icebergs are created. And there's a pretty, actually kind of want to show you this video. I'm kind of wondering if I should just bring up YouTube and show this to you. It's a pretty amazing event. Kind of wonder if I should just go on here and show you this. But it's pretty neat. Yeah, so I'll show you this. This is what glacial calving looks like. I'll try and turn this up really high so you can hear this.
Regular check-ins. Just nothing's happening.
Whoops. Turn up the volume so you can hear it better. So this is a calving event. This is what happens when sea ice or glacial ice starts to meet the ocean, and it calves off into the ocean. So it splits off into the ocean. This is a natural process. It happens. It's not something unusual per se, but it happens every day.
Holy shit, look at that big bird rolling. All forward right? Look at that. You see look at the whole thing.
You can see all the glacial ice falling into the sea. Look at this huge chunk of ice. You can't imagine. So you can't imagine how large this actually is, because you don't have any perspective when you're looking at this video. What he's going to do is he's actually going to superimpose a scale for you to see, just so you can get an idea how large this is. This is like the island of Manhattan falling into the ocean. It's that magnitude of event. So you can see the oceans rolling and roiling over. Just massive amounts of ice are calving into the oceans like here. Look at that. It's like a gigantic ice cube the size of Manhattan. It's beyond what you can even imagine. I'm going to zoom ahead here just so you can kind of see what I mean.
We'll resort to some illustrations again to give you a sense of scale. It's as if the entire lower tip of Manhattan broke off, except that the thickness, the height of it, is equivalent to buildings that are 2.5 or 3 times higher than they are. That's a magical, miraculous, horrible, scary thing. I don't know that anybody's really seen the miracle and horror of that.
Yeah, he's right. It's awesome. It's just a really awesome event that was recorded on screen, and it's just boggles the mind how large it was. So it's not like those things. It's like the end of the world, it's a totally natural process that happens at a glacial calving. It's just what happens when glacial ice flows and eventually it meets the ocean. It flows downhill, it meets the ocean, and it breaks off, becomes an iceberg. So pretty amazing though. So let's move on to the Antarctic ice sheet. So the Antarctic ice sheet is obviously in Antarctica. Okay, you can see again the very tips of these mountains just poking through the ice, because the ice is so tall. You know, the ice is maybe in some places 5,000 meters thick, right? So 5 kilometers. It's tremendous, you know, tremendous. It's 5 kilometers is what? It's 17,000 feet, something like that. So very, very thick ice. This is what Antarctica looks like, okay? It's a continent. There's actual continental landmass underneath the South Pole. That's different than the North Pole, because on the North Pole, there's no land. You know, there's no land in the Arctic. It's all just water. And so the ice that is there is floating in the water. That's not the same with the Antarctic. Okay, there's actually a continent under there. There's you know, fossils and mountains and everything else under there, just like we have on land. So you can see that there's ice shelves here. These are places where the ice is forming over the water, even though it's technically continental ice. Okay, it's just sort of a shelf over the water. There's mountain ranges here that, like I said, the Trans-Antarctic Ridge, that are poking through the ice in the highest points. Yeah, so these are different ice shelves here, the Ross and Larsen ice shelves, the West Antarctic ice sheet, and the East Antarctic ice sheet. Okay, so these ice sheets are very, very large, you know, thousands of kilometers across, thousands of kilometers deep, and not kilometers, thousands of meters deep, and they feed into these ice shelves and ice streams that eventually reach the ocean and calve off like we saw in the video. Okay, so there are 2 ice sheets. You need to know that, the Greenland and the Antarctic. Okay, now let's move on to alpine glaciers. So alpine glaciers are glaciers that form on the tops of mountains, and they can form anywhere. They can form near the equator, like even on Kilimanjaro in Africa, near the equator, we have a glacier, right? So you can have glaciers form anywhere. You know, even like I said, near the equator, as long as they're sufficiently high. So to have an alpine glacier, you have to have 4 conditions. First of all, it has to be cold enough that winter snow does not completely melt during the summer. So that means the elevation has to be high enough to keep that low temperature, because you know it's colder as you get up higher into the atmosphere. There must be sufficient snowfall. So there must be enough winter precipitation for a thick snowpack to accumulate. Now, another thing is the slope must be gentle enough that avalanches don't carry the snow away. Because if you have a really steep slope, you know, and every year you get glacial ice forming, you know, maybe you have enough snow that you get a nice snowpack forming up here. But if the slope is too steep, avalanches will just carry that material away to a lower elevation, where it will just melt away. Okay, so you have to have a let me erase the ink on here. You have to have a slope that is high but kind of gentle. So you have to have something that's kind of, you know, it's going to be high enough, but it's going to have a relatively gentle slope, right? So that could work, whereas something like that would be too steep, if that makes sense. So another thing is time. You just need to have time so that you get enough mass building up that you start to get a downhill flow of the ice. Okay. So alpine glaciers do something kind of interesting. They mass balance. So there's going to be a place where they start to accumulate mass that's on the top, and there's going to be a place that, you know, they're going to be flowing downhill. They're going to be bringing that ice to lower elevations where it's going to melt away, and you're going to have this kind of equilibrium point where the glacial ice is accumulating in one place called the zone of accumulation, another place where it's melting called the zone of ablation. Okay, so in this area, you have the zone of accumulation where ice is building up high in the mountains. It's going to flow downhill every year. It's going to be flowing, flowing, flowing. And once it gets low enough elevation, it's going to start to melt in what's called the zone of ablation. And then you're going to get loss of ice by meltwater. So the ice is going to be melting, and meltwater is going to form and be flowing out of the toe of this glacier. By the way, this was right here is called the toe. Okay, so this, we're gonna have this constant mass balance. We're gonna have what's called an equilibrium line, where and that equilibrium line can either move up or down if the glacier is receding or if it's advancing. And the equilibrium line is where there is no gain and no loss year after year. So how do glaciers move and flow? So I want to make it clear that glaciers don't, the flow of the ice and the movement of the ice is not so much like, don't think of it as so much scooting along the bottom. Glaciers do scoot a little bit along the bottom, but also the glacial ice is flowing. It's literally moving and flowing like a stream. It just does it very slowly. Okay, so near the ground, the friction slows the ice down, but as you get higher and higher into the profile, the glacial ice can move. Now, as it scoots and flows along the ground, it's going to pick up lots of sediment. It's going to erode, and glaciers are some of the most effective agents of erosion on planet Earth. So they will pick up rocks, boulders, clay, sand, anything, and they will be grinding them along the ground as they flow. And so they almost act like these big, you think of like a massive sheet of sandpaper moving over the land, and they will polish, they will grind, they will scratch the surface as they flow. So here's another picture again, a picture that's, or a video that is, what do you call it? It's where they take the same picture, time lapse. It's a time lapse photo showing the movement and the flow of the ice. And again, this isn't a river. These are glaciers. And you can see the tributary glaciers flowing like ice streams into a main branch, right, that is flowing into the ocean eventually. So these work just like streams. And just like streams are erosive, so too are glaciers highly, highly erosive to the landscape. Okay, so you can see places where grooves, these deep dramatic grooves, have been carved out by glaciers. These look at this, pretty cool looking. It almost looks like someone carved like a track or something into the rocks. It's all from glaciers just moving over the surface. Okay, so these are other features left over by glaciers. These are called glacial erratics. They're large, sometimes the size of school buses. Large boulders that are left over from glaciers. One thing that's kind of interesting, if you ever go to New York City and you probably think like New York City is one of the last places you're going to observe much of earth science, but Central Park in New York City is a really great place to observe a glaciated glacial landscape. So there's a lot of features in Central Park, like they have glacial erratics. Like this boulder got here because it was dropped by glaciers that were left over from the Laurentide ice sheet 14,000 years ago in last glaciation. So that's how sediment is moved by glaciers. It picks stuff up, it flows, and it grinds it along the surface. But it picks up a lot of sediment, it deposits a lot of sediment, and it erodes the hell out of the landscape underneath of it. So you get these places where there's glacial polish, where you get almost like a mirror-like finish to the rocks that glaciers have moved over, because it's polishing them with the sand grains, clay, sand, silt grains that are carried along with the ice. Okay. So all these things, these little features of where the rock has been plucked up like this is called Rouche Montagne. They're pretty cool because you can actually tell the direction of movement of the glacial ice. So whatever, you can actually figure out that what direction the ice was moving at that time. So the ice in this time in Central Park was moving in this direction, as you can see. So the kind of more shallow slope, and you can see a steeper slope on this side. The ice is moving over this shallow slope and leaving. That's like kind of on the iceward side, and the leeward side is this more or steeper side. Okay, so that's called Rouche Montagne. Gives you the direction of ice flow in a particular area. So glaciers are not like bulldozers. It's not like they're pushing sediment like this. They are more like conveyor belts, okay, of flowing ice. So they pick up sediment and they move it to the toe of the glacier and they deposit it in a big pile at the toe of the glacier. So that toe, that pile of sediment that forms at the toe, the terminus of the glacier, is called a moraine. And you get these vast moraines that are left where glaciers were at the toe of the glacier as it was receding. Okay, so you'll get these big piles of sediment. You can see a pile, a ridge here, a ridge of sediment here, a ridge of sediment here, and it shows at different times this was the toe of the glacier. So it's kind of cool because when you see things like this, it shows you how much the glacial toe has moved over time. You can see that this glacier has been receding because you see a terminal moraine here, a terminal moraine ridge here, and a terminal moraine here. So a moraine is just a ridge of deposited sediment at the toe of a glacier. Okay, and it gives you some history of the glacier movement and recession, or as it were, the advancement. It's kind of cool because you can find moraines all the way far south as Ohio that were left from the Laurentide ice sheet. They're 14,000-year-old moraines that are left over from that last massive glaciation we had in the Ice Age. Okay, so you have got tributary glaciers. They feed into a valley glacier, which is a larger glacier. It's all flowing downhill, so you can see all these tributary glaciers that feed into this larger valley glacier. Okay, and those things will leave what are called medial moraines that are kind of in the center of the median, the center of the valley glacier. So moraines, they're poorly sorted glacial debris. We call any, by the way, any sediment that is left, this is important because I have some questions about this on the lecture assignment and also on the test. Any sediment deposited by a glacier is called till. Okay? Any sediment that's carried by the ice is called till. So it forms these ridge-like deposits of till at the terminus, the toe, and at the edges of the glacier. Okay, that's what a moraine is. Basically, they're going to look like these big hills and piles of sediment that are very, very, very poorly sorted. So also, let me go over some just sedimentary sediment terms here. Glacial drift is any sediment that is deposited by glaciers, whether it's meltwater from the glacier or whether it's the glacier ice. Okay, so glacial drift is there's two types of glacial drift. There's glacial till and there's glacial outwash. Okay, glacial till is deposited by the ice. Glacial outwash is deposited by the meltwater that is flowing out of the melting glacier. Okay, glacial till is unsorted, very poorly sorted, because it's deposited by ice, which is a very poor sorter of material. Glacial outwash is very well sorted because it's deposited by the water, not the ice. Okay, these, by the way, form some of the best deposits of gravel and sand that we have in this country. So when you want very nicely, sorted deposits of sand and gravel, you can go to these glacial outwash areas. So what do you think? What does that look like? Does that look like glacial till or glacial outwash? So hopefully looking at this, you'll say till, because you can see the material is very poorly sorted. You have boulders mixed in with sand and silt and clay. This, on the other hand, is obviously glacial outwash, because you get this highly stratified, that means a lot of bedding in it, beds of more well-sorted material. You can see some of this, it looks like pure sand, some of this on top looks like pure gravel, stuff like that. Okay, so that's glacial outwash deposits. The kind of landscapes that get shaped by glaciers are very dramatic, very beautiful. They're also very characteristic. You can go into an area after taking this class. You can hopefully, when you go into a new area, you can sometimes tell if there have been glacial action in that area. This is a very beautiful picture by John Muir. He's a very famous conservationist, naturalist, and a great American artist who took a lot of photographs of the national parks. So this is a John Muir photograph of the Snake River, beautiful Snake River in the Grand Tetons, one of the most beautiful areas of this country, I'd say. Close second, or maybe a first, is the eastern Sierra Nevadas are also a very beautiful part of this country. So I hope you get a chance to view those areas someday. This is the Snake River. Also, if you're into trout fishing, this is just a world-class trout river. If you like to fly fish, or if you like to even to bait fish, it's a great place for cutthroat trout, and really a fabulous area if you ever get to visit this. And someday I do want to figure this out and take students on a field trip to Del Mar College students on a field trip to this area, because it's really a beautiful, majestic area. But these are the Grand Tetons that are you'll see are very characteristically been shaped by glaciers. So I don't know if any of you recognize this little thing here. If you grew up in Southern California, you probably know what this is. This is the Matterhorn in the Swiss Alps. I'm saying if you grew up in Southern California, you might be like, what does Southern California have to do with the Matterhorn? The Matterhorn's in the Swiss Alps in Switzerland. Well, Disneyland, California, has a scaled down replica of the Matterhorn. It actually looks quite a bit like the real thing. So this is the Matterhorn. Horn is a very sharp peak that has been carved out by glaciers. So the way that this works are the glaciers are kind of surrounding this mountain on either side, and they're carving it and whittling it down until it becomes a very sharp, angular point. That's called a horn. Okay, so we're going to talk about cirques, arêtes, horns, hanging valleys, and U-shaped valleys. So you can imagine that prior to glaciation, you might have a typical V-shaped valley formed by a river. So you can see the shape of this valley is like a V. Once a valley glacier fills it during a period of glaciation, you have these these tributary glaciers filling into a valley glacier. The valley glacier makes a much broader erosive shape to the valley, and then you can see it's more of a U shape instead of a V shape. See, that's a classic V shape, right? This is, on the other hand, a U shape. So if that glacier melts, you're going to have this broad valley with very steep sides. That's called a U-shaped valley, okay? And then what happens is you get these old tributary glaciers. You get these little U-shaped valleys that feed into a larger U-shaped valleys that are hanging above the main valley floor. Do you see how these are kind of elevated above the main valley floor? And you get these beautiful waterfalls that fall into the main valley floor below. So those are called hanging valleys, U-shaped valleys. This is a classic U-shaped valley in Yosemite, California. Okay, and Yosemite is yet another beautiful area that you should visit someday. That's a U-shaped valley. You can see that there is another tributary glacier. So there used to be a big valley glacier that was filling this in. It's gone now. It went away with the last ice age. There's now a U-shaped valley, a hanging valley that is feeding into it with these majestic waterfalls feeding into it. You can see that's beautiful half dome way down there in the background. So that is a U-shaped valley, very classic U-shaped valley, hanging valley right there. And let me also show you some things of horns, arêtes, and cirques. So as you get these tributary glaciers forming off of a peak, you can see that the peak is sort of surrounded by these tributary glaciers that are moving off of the peak. And what happens is these tributary glaciers form kind of these amphitheater bowl-shaped depressions right here that are called cirques. And they sharpen the point of the mountaintop, and we call that sharpened mountain point a horn. And these ridges, you can see these sharp ridges that are flowing from the horn, or attaching and flowing outward, radiating from the horn. We call those arêtes, okay? So there's a cirque. Okay, these are cirques. Arêtes are these ridges. Ridges. Horns are these peaks, okay? And these little lakes that form in the in the cirques I'll call Paternoster Lakes. I don't know where they got that name. Paternoster is, of course, Latin for our Father. So I don't know where they got that name. It's kind of interesting. I have to look that up. So this is a river valley before and after glaciation. You can see it starts off as a V-shaped valley. Okay, you can see a little V there. And as it gets glaciated, it fills in, it erodes, and as the glaciers recede, you get a U shape instead of a V shape. Okay, and you can see now you have a horn here. You have a ridge that's called an arête. This is going to be a cirque right here. Okay. You can see this is going to be a hanging valley. Right, you can see the hanging valley there. These are the Paternoster Lakes that form up there. Okay, so let's take a look at these, just review over these erosional features. So this is a horn, right? These are arêtes. These are cirques, arêtes, arêtes, arêtes. This is a little horn back here. That's a horn. Okay, that's a U-shaped valley right here. It's a U-shaped valley. I'm just kind of going over a lot of stuff, right? There's the terminus, the toe of the glacier. There's the meltwater coming out over the outwash plain, depositing well-sorted material and outwash sediments. You have a moraine left here, right? This is the zone of accumulation, the zone of ablation, tributary glaciers feeding into a valley glacier. Okay, a cirque is up here, the cirque basin is up here, horns are here, arêtes are here. So I'm just kind of going over all these different features you should know. Yeah, I think that's all I can really think of here. I want to say. So I think I'll stop. I think you got it all. So hope you enjoyed the lecture. And let me know if you have any questions. Just turn in your lecture assignment this week. And I hope you have a good one. I'll talk to you next week.